Now that NoC-SE has generated the topology, let's switch to the Canvas tab. The tool provides two canvas views, the logical canvas and physical canvas. The logical canvas presents a compact, diagram-style view of microarchitecture components and their connections. It focuses on the logical topology rather than physical implementation, so it does not display the actual locations of the components. This view makes it easier to understand the overall connectivity and to modify microarchitecture parameters. The physical canvas provides a more detailed view of the microarchitecture. It shows the physical locations of the components and their connections. This view is intended for physical optimization tasks, such as relocating microarchitecture components, adjusting the floor plan, improving time enclosure, or addressing other physical design constraints. Let's begin with the logical canvas. We can expand the right-hand panel by clicking this arrow. Here you will find the different editors and viewers. At the top is the Canvas Visualizations pane. The canvas is made of different layers or networks. You can only edit one network at a time, which you select in the Edit Network field. However, you can display multiple networks simultaneously by selecting them in the Visible Networks field. Before making any changes, make sure you selected the correct network to edit. If you can't see a component that you expect to be there, it is usually because the corresponding network is not currently visible. For example, we can't see the MCNs in the current view, but as soon as we make the CHI network visible, they appear. Select any component on the canvas to display its properties in the property editor on the right. For example, let's click on ASNI 0. The property editor now displays the configuration for this interface. You can expand each section to view additional microarchitecture parameters and modify them. Before making any changes, it is recommended that you create a checkpoint. This allows you to restore the current design state if necessary. To create a checkpoint, go File and then click Create Checkpoint. The tool prompts you to save a YAML file in your project directory. Enter a name for the checkpoint and then click Create Checkpoint. The checkpoint is now saved. Now let's modify one of the ASNI microarchitecture parameters. Expand ASNI interface parameters in the property editor. For this example, assume that an additional retiming stage is required on the read response channel on packet tracker path in order to meet timing. So let's enable egress register 1 to break the timing path. Select this option, then click Update to save the changes. Adding the egress register increases the round-trip latency. To compensate for this additional latency, let's increase the channel credits for the read response channel. To do this, select the connection between ASNI 0 and the router. In the property editor, click Connection Parameters to open the configuration dialog. Increase the read response channel credits by 1, then click Update to save the changes. You can use the same approach to modify other parts of the NoC-SE generated topology and further optimize the design for your implementation requirements. Once you finish, don't forget to save the configuration. Now, let's look at the physical canvas. This view is similar to the floor plan tab we used during the NoC-SE configuration. The difference is that now it's populated with the microarchitecture components and the endpoint interfaces are routed. For this demonstration, let's assume that DSU is located far away from the MCN. To help meet timing, we will insert device credited slice DCS into the CHI network. Before adding DCS, we need to select CHI in the Edit Network field on the right panel. Next, let's expand Design Process Microarchitecture in the left panel. This section provides the microarchitecture flows for the CHI network, along with the components that you can add to the design. One of these components is the device credited slice DCS, which you can drag onto the canvas. But before placing the DCS, let's remove the existing connection between the CDB and CAL. Select the connection, then click Remove Connection in the Connection Editor. Now let's drag the DCS onto the canvas. and assign it to the appropriate clock domain. Next, use the connector tool on the Canvas toolbar to connect the CDB to DCS, and then connect the DCS to the CAL. Notice that these connections are displayed as dashed lines rather than solid lines. Dashed lines indicate that the logical connection exists, but the routing has not yet been assigned. To assign the routing, open the root editor next to the property editor, select the CHI network, and click Refresh Routes. The routes between DSU and the CDIs are marked with the yellow assign status, indicating that routing still needs to be assigned. Compared to this, other routes which are already assigned are shown with the green status. You can assign each route manually by selecting it and choosing one of the available route candidates. Alternatively, click Auto Assign to allow the tool assign the routes automatically. You can also run the Route Analyze tool from the toolbar, which I mentioned at the beginning of the video, to achieve the same results more easily. Finally, validate the microarchitecture by clicking MicroArch to run the microarchitecture design rule check. The design passes the validation, so we are ready to move on to the next stage.